In question number 8, we are asked to find the values of y and z that allow these points P, Q, and R to be collinear. In other words, we want them to all lie on the same line in space. So I'm going to do this using vectors. What I'm going to do is I'm going to construct the vector P to Q and the vector from Q to R. And then if these 3 points are collinear, if they all lie on the same line, these 2 vectors are going to have to be parallel, which means that one is just a scalar multiple of the other. Alright, so the vector PQ would have components 2, -1, 2, and the vector QR would have components 4, y minus 4, and z minus 2. So if one of these vectors is a scalar multiple of the other, that means that constant of proportionality is going to have to be the same for these two components, and these components. What I'm getting at is that this component is twice this component. So this one must be twice that one. This z component must be twice that z component. So y minus 4 is going to be 2 times minus 1, again because 4 is 2 times 2, and we want that same proportion all the way through. And z minus 2 is going to be equal to 2 times 2. So this tells us that y minus 4 is equal to -2, or y is equal to 2. And here we get z minus 2 is equal to 4, or z is equal to 6. In number 9, we're told that the planes 3x plus 2y minus 5 equals 0 and x minus y plus z minus 1 equals 0 intersect in a line containing the point 1, 1, 1. And what we want to do is find a set of parametric equations for the line of intersection. So to find parametric equations, we need not just a point on the line, but direction numbers for that line. In other words, we need a vector that is parallel to that line of intersection. So here's what we're going to do. Imagine 2 planes, let's call them maybe P1 and P2, intersecting in a line. We're given a point on that line, and what we need to do is find a vector that's parallel to that line of intersection. Well, one way would be to just find another point on the line and then construct the vector from the first point to the second, and that would be the vector that we needed. But another way that we can do this is with the cross product. So here's what I'm going to do. Let's look at let's consider rather the normal vectors n1 and n2 of these 2 planes. By definition, any vector in the plane P1 is going to have to be orthogonal to the normal vector n1. Similarly, any vector in the plane P2 is going to have to be orthogonal to the normal vector n2. Well, the vector that we're interested in can be thought of as lying on that line of intersection. That means it's on plane P1 and plane P2. So this line is going to be orthogonal to this vector, but it's also going to be orthogonal to this vector. So what we need for our direction vector is a vector that is orthogonal to both n1 and n2. Well, you might remember that when you take the cross product of 2 3-dimensional vectors, you get a 3-dimensional vector that is orthogonal to both of the original vectors. So that's our method of attack. So let's find the cross product of the normal vector here and the normal vector here. So remember that we can do that, or we can find these normal vectors by just reading off the coefficients of x, y, and z. So for this plane, the normal vector would have components 3, 2 and 0. The coefficient of z is 0. Here the coefficients of x, y, and z are 1, -1, and 1 respectively. And so we can find this formal 3 by 3 determinant, and that'll be the cross product. Okay, so I'm going to do this by expansion along this row. So I need I times this 2 by 2 vector. It's 2 by 2 determinant. Well, this 2 by 2 determinant would be 2 times 1 minus -1 times 0. That would be 2 minus 0. Then we need minus j times this 2 by 2 determinant, 3 times 1 minus 1 times 0. That's 3 minus 0. And then plus k times this 2 by 2 determinant. And so this can be 3 times -1 minus 2 times 1. So that would be -3 minus 2. So I'm getting the vector 2i minus 3j minus 5k. That's our direction vector. And so the direction numbers are 2, -3, and -5. Alright, so to form the parametric equations for this line, we're just going to write a parametric equation for each variable x, y, and z. So remember, we're thinking of this given point as sort of the starting point, and so x, y, and z each start at 1 in this case, and then they increase or decrease proportionally according to the coefficients of that direction vector. So we would have plus 2t minus 3t minus 5t. This is not the only possible answer. For instance, you might have found the cross product using the opposite order from what I used, and your cross product would have would be -1 times the one that I have. And there are other possibilities for that vector. But this is one solution. Here we're going to find the area of the triangle defined by 3 different points. So we're going to do this using vectors. So I need 2 vectors for this. What we're going to end up doing is finding a cross product. So we need 2 vectors from these 3 points. Now you can use PQ and PR, or QR and QP. It does not matter. PR and QP, any 2 vectors from these 3 points will be fine, as long as you don't use something like PQ and QP. Alright, so the idea here is that if you take 2 vectors, and I guess I'll go with PQ and PR. If you take the cross product of those 2 and then find the magnitude of that cross product, what you'll end up with is the area of a parallelogram. And so what parallelogram am I talking about? Well, if you take another copy of this vector and put it down here, and another copy of this vector and put it over here, the 4 vectors will form the edges of a parallelogram. And again, to find the area of this parallelogram, we find the magnitude of the cross product of 2 of these vectors. But we only want the area of a triangle, which is half of the area of this parallelogram. So let's do this. The area will be 1/2 the magnitude of the cross product of PQ and PR. Okay, so let's figure out what PQ, what the component forms of these 2 vectors are. Alright, so for PQ, we're going from here to here. Let's see, and going from P to Q, the X component does not change at all. The Y component grows by 5, and the Z component grows by 2. From P to R, the X component shrinks by 6. The Y component shrinks by 6. Is that right? No, the Y component grows by 6, and then the Z component grows by 6. Alright, so now let's find the cross product. The order here doesn't matter since we're going to be finding the magnitude anyway, and changing the order in the cross product does not affect the magnitude, only the direction. Alright, so let's expand along that top row. So we'll have I times negative 30 minus 12. Sounds like negative 42. Then we'll have negative j times 0 minus a negative 12. And then finally we'll have k times 0 minus a negative 30. So that looks like it's going to be negative 42i plus 12j. And then I think it's, is it plus 30k? No. That's going to be minus 12. Alright, so what we need to do then is find the magnitude of the vector. And I'm going to switch over to the other notation. So that would be the square root of 42 squared. The signs don't really matter since we are squaring. Now those are awfully big numbers for me to try to handle in my head because I'm not using a calculator. So I'm going to use this trick instead. I'm going to factor out a common factor of 6. Now, if we can figure out the magnitude of this vector, we can multiply that magnitude of 6. We can multiply that magnitude by 6 to get the magnitude of the entire vector, which is equal to this vector, right? So remember that multiplying a vector by a constant scales the magnitude of the vector by whatever that constant is. So multiplying this vector by 6 will multiply the magnitude by 6. Alright, so let's take a look at this. We're going to get 6, and then we're going to have the square root of 7 squared, which is 49, and then 2 squared is 4, and 5 squared is 25. So that's 6 times the square root of 53 and 25. I think that's 78. And those are much easier numbers to work with. Now, we're not quite finished because this is just the magnitude of the cross product. That's the area of that parallelogram. This parallelogram. So we need to divide by 2. And that will give us an area equal to 3 times the square root of 78.